Thank you very much. I'm very honored by this invitation. I'm much of a computer science like Torsten is, less inferior one compared to him, but nonetheless. First I'd like to talk about the important subject matter of what Fugaku is in a very broad scale, how it came about, and also what is important. But I think the most important subject matter that was brought up this morning was the fact that how, in order for the climate community to have sustainable impact, it's important to make sure that it has sustainable economic story, and that's what we also aspire with Fugaku, not just to build a very large and fast machine, but make sure that it provides sustainable economic prosperity to the society, and we try to quantify that as much as possible, as you will see. Okay, so first, this is a machine, I'm standing in front of it, so it's hard to get a perspective of how big this machine is, but you can go to our website and look at there's a 3D virtual walkthrough of the machine. So the machine is about 3,000 square meters in area, has 432 cabinets, has almost 160,000 nodes, each with 1 terabyte per second HBM attached to it. Although LIMPAC, we go to about 30 megawatts. In normal operation, we operate about 16 megawatts, which is 100 watts per node. So we could have built a machine twice this size, and still will have been below our data center capacity. We just ran out of money. We have 163 petabytes of memory bandwidth. To put this in context, this is 1,000 times more memory bandwidth compared to the Earth simulator. So, so it's very good for like transport equations for climate weather codes. And still the fastest with respect to that. And you can do a virtual walkthrough. You can look at the status of operation on Fugaku, including how green we are. So that's that. And all the specs for all the people who love to look at machine specs, like people like nerds like me. So we're essentially an exascale machine in various precisions. And but the more important part are for the climate community, of course, and the weather community are the memory bandwidth, the network injection bandwidth, and so forth. And then those we have plenty. We provide about 1.3 billion node hours to the community, some of which, of course, is used for climate weather. And we have collaboration with many institutions globally, including the major European centers, U.S. centers, Asian centers, and also some weather and climate center like ECMWF and so forth. So, and to demonstrate how powerful the machine is, compared to other machines in the world, of course there are other institutions now putting up excellent machines, like the U.S. has Frontier and LIMPAC, which goes to about 1.1 exaflop. We're not that up to that extent because our machine's older. But in terms of APCG, which is of course important metric for any of as far as matrix goes, then we're still on top compared to Frontier. And there are other types of metrics, and we're number 1 in some of them, we're number 2 or number 3 in others. Here, MLPerf, NVIDIA has a better machine, but we're largely up there in terms of being one of the largest machines in the world, especially for climate weather community. This enormous memory bandwidth that's designed into the system could be very attractive. Now, of course, Fugaku wasn't developed to satisfy these benchmarks. It was really designed over a decade, looking at the goals, the societal goals as imposed by these very important areas of science and technology. So things like health and medicine, environmental disaster, energy, materials. Of course, we have meteorological low environment predictions, and that was one of the biggest areas, co-design and application readiness program area. And the objective was to achieve over 2 orders of magnitude speed up over the K computer, which was the predecessor. But also, you might notice that a lot of these areas are not pure basic science. There's one pure basic science here, but a lot of these are pertinent to sustainability. In fact, all except this is pertinent to sustainability, because these are like medicine, pharmaceuticals, and medical types of applications, biology and others, and those types of applications. But even if you take a look at things that pertaining to climate change, direct simulations of climate, and also mitigations of disasters caused by climate change, or how to reduce carbon dioxide emissions. If you include those types of application areas, it actually spans across many of the areas where Fugaku is targeted to excel. Okay, so it's always the application first philosophy with which we built the machine, never for things something like LIMPAC. Okay, so and now as a center, we don't just build build machines. We are pursuing various aspects of how we build a machine, science of computing, science of hypercomputing, how we'll build the next generation machines, how we build the next generation of AI models, and how we support it with our hardware underneath, how we build effective quantum HPC hybrid system. And I have no time to go into these today, but if you're interested, you can ask me. We'll probably have the world's largest quantum testbed in the upcoming months, with lots of 100 qubits class machines on premise hooked up to Fugaku. But then we also are tasked at doing science by computing, science by AI, which of course some of the subject matters that Jensen also presented this morning. Excellent talk, as always. So we have a very comprehensive center, laboratory or center, that work all within ourselves in collaboration on the system side and application side, but also with the entire Japanese and also international community. But before going to that detail, just to show you how it has been important to not only affect the society, but also to quantify the effects of high-performance computing, how it benefited the society. Because it always asks, when we talk to politicians, like the one just came on, not the German ones, the Japanese equivalents, they always ask me questions, okay, we invested all this money, what do we get in return? Okay, that's the important thing. So I'll just give a very short exemplar of our COVID program, which kind of happened when the COVID pandemic happened, just as we were installing Fugaku. And we took the opportunity to launch all these comprehensive sets of COVID programs, mitigation programs that exploited major portions of Fugaku that was being built up, because the machine was still being built up, so we only had hero users. So these people added to the list of portfolio of hero users, in fact, given even more special privileged treatment, so they can effectively use the Fugaku, which was already the fastest machine in Japan, but use major portions of them. And they range from things like very, very molecular level studies, but one of the most famous studies that was undertaken was the aerosol, droplet aerosol simulation, which was never done at this resolution or at this scale before, in order to simulate, create digital twins of societal situations, and by which we could have a very quantitative assessment of the risks and what kind of mitigation measures would bring down the risks, again, by measurable quantitative metrics. Then we had this, also had this economics assessment of or societal simulations of what the pandemic have been causing, but I'll get to that right after I describe this one, which won the Gordon Bell Prize for the pandemic, for the COVID-19 in 2021. So I don't have time to go into detail, but essentially what we had done is create over 2,000 digital twins, simplifying very typical COVID transmission scenarios, all the way from fairly low to very detailed resolution, like various sorts of masks and the materials, to a larger societal situation like concert halls and also things like classrooms and office space and transportation vehicles, and all the way down to the microscopics of how these transmissions occur from aerosols being emitted from your mouth. It's doing some of the biological simulations. All these accumulate to over 2,000, and we got cases, more than 2,000 digital twins, and this occupies significant portions of the Fugaku cycles that were available. But this helped to mitigate COVID in a significant way because people trusted supercomputing, fortunately. We had a very educated society. In fact, we had, maybe they were too educated, but there was some blind trust about supercomputing, that these were real science. But people were able to use, as soon as, for example, we would have a press conference about our latest findings, we have a press conference, over 100 media people will come, and immediately in the afternoon, we have a press conference in the morning, immediately in the afternoon, you watch the TV, they're everywhere. So, this is the latest COVID-19 mitigation measures as announced by Fugaku. And people wore masks and did ventilations and took lots of preventive measures to allow them to, so Japan had one of the lowest COVID cases in the world, this pre-vaccine days. And so what was the effect of this? Well, of course, obviously it saved a lot of lives, but we also did a very detailed economic study, quantitative studies of how this lockdown would, however, in Japan, the degree of lockdown was much less than the European countries where people were not even allowed to go out of their homes, but rather Japan had a lot weaker lockdown, but people took more preventive measures. And this allowed, and we did a very detailed economic study looking at every company in Japan, basically, and did basically very detailed microeconomic analysis, and then came to the conclusion that having a full lockdown like Europe would have followed this curve in terms of a downturn of GDP. But because of the more relaxed measures, it was only this green line. And this largely matched the estimation by IAIA with respect to the economic downturn that we had suffered, only by like 1 or 2% difference. So showing something like this to the politicians, they really say, oh, you saved us like billions of dollars in terms of GDP downturn. So thus, supercomputing is worthwhile. And this is exactly the sort of thing we continuously have to do in order to justify that supercomputing will benefit the society. Right? And this is what we're continuously doing. And in fact, we commissioned Hyperion, which is one of the two major consulting companies globally. They consult many supercomputing centers. They used to be part of IDC, which did consulting for the global IT market, so they're very trustworthy. They have lots of data. And recently, they filed a report for us saying, so what's the economic impact of Fugaku overall? Not just COVID, but across in many industries, industrial applications, and so forth. And the conclusion they came up with, and of course, we didn't affect them. We helped them get the data, but we didn't affect the results, was that the Fugaku, compared to the investment, which is about $1 billion euros, will return about 68 to 90 times its cost, which is, of course, up to 90 billion euros. Of course, I'd like to believe that, obviously. They don't pay me as well, but so the return on investment, which is about over $100 billion in US money, is enormous. But so that's the quantitative measures numbers they came up with. We're doing some studies on Fugaku, doing Fugaku itself to do the economic analysis to justify the fact that Fugaku is worthwhile investment for the society. These billion-dollar investments are worthwhile for the sustainability of society itself. Okay, so getting back to the business of research. So this is my center, and we have these people on the application side, science spy computing, and we have people like Tomita Yusama, whom you might know, or Takema Sumiyoshi, who's a leader, who has one of the leaders in data assimilation, and we have a whole bunch of other people on the application side also that's doing the basic something related to climate, weather, and also things like disaster mitigation. So these are the team leaders, but we'll also have collaborations with lots of external entities. For example, Tomita-san has a collaboration with ECMWF and so forth. So one thing that Tomita is doing, their team is doing is to really look at the basics of the climate models to build the foundations, not only to do the research themselves, but to build the foundations. So they have a new code. They had a code, RIKEN, which was one of the major codes, and which is used very often in Japan. But now they have for exascale, they have a new version, which is called Scale, which is it's a library, but it's much more amenable to scaling over exascale machine. And then they're trying to incorporate new types of models, going from standard LES using the triangular meshes to more cube spherical grid, but going to DGM or discontinuous Galerkin methods for exascale machine. It seems their conclusion is that this gives you much higher resolution at lower computational costs, provided you have enough localized bandwidth in the system, and that's how we're designing the next generation machines, circa 2029 or something. So it's, again, there's a co-design being involved where there are fundamental changes, where we're looking at fundamental changes in the underlying like transport codes in the model itself, and so we have some very bright young people doing that, things like that. But in terms of application, going directly back to application, so Japan's Meteorological Agency, they used to be very much isolated. They had their own supercomputer. Of course, there was some collaboration, but they always insisted on using their own machine. It was very hard to collaborate with them. But now they completely changed with the last director, Director Hasegawa. And he really said, well, there's a machine, Fugaku, out there. We have excellent people like, there at Jamstack, we have Tokyo people like Professor Sato's group and so forth, so you guys go and collaborate with them. Because there was a significant occurrence of these torrential rains caused by this very sudden appearance of rain bands, very high concentration. And it seems that there is no English terminology for this. It's called senjoku suitai. But nonetheless, this is a very, very chaotic phenomena. It's very hard to predict with their traditional models. So they had to go to lower resolution. They had to put new physics in. But they're very successful in doing this using Fugaku because they were given freedom to do so. In fact, they were so happy with the results that they were able to justify to the government, well, we have our standard forecast machine. They just were renewing, but we need additional machines. And we need a copy of Fugaku to do the actual forecast. So what they successfully got two machines, this and this one, which are actually the same one, but of course they're doing forecasts professionally, so they need two machines, or obviously. So they bought two machines to about 1/15 of the size of Fugaku for doing day-to-day forecasts. So now they have four machines. They have two to do the normal forecast, which is more of a Xeon, standard Xeon machine. But now they have copies of Fugaku, two machines there, to do these extreme weather type forecasts. And they're spending, $100 million, 100 million, something like that, in order to facilitate these. And now they're starting forecasts of these rain bands starting, I believe, this month or so. Yeah. Okay. And then there's an issue of doing even more accurate weather type forecast, because weather is very important for farming, food, for renewable energy, wind, solar, and of course for disaster mitigation like the one I showed you. And we're putting a lot of emphasis on these real-time data acquisition and data assimilation thereof with very high-resolution weather forecasts. So one experiment that Tomita and also Takamasa Miyoshi's team did is to construct a system where they would do a data assimilation by using a very large ensemble forecasting, 500-meter resolution, 30 minutes ahead, 30-second interval. But by doing data assimilation with a new type of phasor radar that can cover the entire, lots of hundred frequencies across the entire Tokyo region. Of course, this was very difficult, but they were able to do so. So they did a continuous forecast over the period of the Tokyo Olympics using about 9% of Fugaku, or about 50 million core, about 0.5 million cores, or about something like 10,000 nodes. And then the forecast was multicasted to your, you could look it up on the website, but it was also proactively multicasted to people's phone applications. So the idea was when you're attending Tokyo Olympics, you can download this app, you could get this very, very accurate forecast because it's summertime in Tokyo, you can get these sudden torrential rainfalls. So you can run for cover 30 minutes ahead of time. And so this is like a schematics. You have the radar. There were like almost about 10,000 nodes allocated to this entire, continuously 24/7 for the period of 4 weeks, 2+2, 2 for Olympics, 2 for Paralympics. And this worked very, very well. And again, it was very challenging because the forecast and data assimilation had to happen at 30-second intervals. But with a machine like this, something like this is possible. And now we've taken this result to see, well, what happens if they would be like radars everywhere? So these radars are still expensive, but what happens, can we do more accurate predictions of these adverse weather effects caused by global climate changes if I had a bunch of radars? So we would build these simulated radars in cyberspace. And then they would do the simulation to see if this will provide additional accuracy, of course, with data assimilation. So it turns out that it is so. By putting more radars, more of these radars strategically everywhere within Japan, we can have very accurate local weather forecasts along with data assimilation. So, and now Miyoshi, who is one of our star researchers, he's running a project where what if we can what does it take to change the weather, given the climate change? Can we change the weather strategically and be able to predict their effects, rather than just munging a whole bunch of dry ice over the cloud and not knowing the consequences? Can we actually change the weather, again, given these climate changes, and see if it's beneficial? Because on one end, we want to prevent global warming, but the other is, even if we had global warming, can you control the weather sufficiently in order for us to sustain our society? That's a very important kind of research he's doing for the year 2050. And again, using Fugaku. And there are other aspects like disaster mitigation. This is work done with our tsunami team and Fujitsu and others, where we would do, this is combining surrogate AI to simulation, just like what Jensen had presented. So you would do a significant tsunami simulation. Again, tsunami will be more frequent, likely more frequent with rising tide levels. But what would be the effect when earthquake happens? Well, we can do lots of simulations, but it's hard to do this in real time, so we'll build surrogates using beforehand. But then we can have a very, very detailed regional prediction of when tsunami happens. We get the data from the tsunami sensors offshore, and then predict exactly how the water will be seeping in, and again multicast this on your smartphone, which has your geographic location. So this application has already been built. It's not downloadable yet, apparently, but once this system is in place, you can tell every person in the region to run for cover, because it'll be the smartphone will tell you, run this way, don't go this way, run this way, and you climb this building, or you go up the mountain and do something like that. And another is earthquake, where we can use hybrid of precision preserving FEM, actually, using a combination of AI techniques, surrogate techniques, and also combine that mathematically sound way to couple that to very accurate finite element method simulation in order to achieve this very detailed earthquake simulation, including tsunami, where it was predicted we need about a 10 exascale performance. But by combining that with AI in a very specific way, we can get thousands of times speed up over K computer, which consists of 42 improvement, hardware improvement from K to Fugaku, but also 25 times improvement using AI techniques. So combining those, we can get 1,000 times speed up, but with precision preserving accuracy. It's not surrogates where you think, you're not quite sure whether you're accurate. This particular solver is precision accurate, guaranteed to be precision accurate. Okay, so you can get 10 exascale, and we can foresee that for the next machine, when we go yet improve our performance, we can get effective zetascale performance by adopting these kinds of combining precision preserving surrogate techniques to the standard simulation techniques. Okay, so that's something that works. For material science, I'll end with a couple of slides here. But these things are also pertinent to things like material science, where again, in order to prevent the emission of carbon dioxide, we need revolutions in the way we produce and store energy. So on Fugaku, we have lots of material science work going on, including material science codes that can scale to tens of thousands of nodes. So this NT-Chem is one particular code, and this allows us to create, do work on things like biodegradable plastic, or use innovative ways to reduce waste in terms of all the biological productions, or produce new types of, let's say, toxicity-free perovskite photovoltaic cells, which is a hot topic, but a lot of these materials used to contain high content of lead. So that's the environmental pollution is a big problem. But now they've been able to produce a combination of AI surrogates, precise, large-scale, tens of thousands of nodes simulation, and also real material generation to come up with new types of perovskite material with 25% efficiency, which could be a game changer because then you can have these perovskite solar cells. You can put them anywhere. You can put them on, you can put them on not only rooftops. You can put them on walls. You can put them on streets. You can put them everywhere. Well, every piece of your land can become a energy-producing location. Okay. So with that, I'd like to. So these are some of the things that are game-changing, but all these things we're trying to attach economic values to, so that we can justify to our politicians that it's not only worthwhile investing into supercomputing and sciences, it's also, but it's a new industry that can generate tremendous amount of value and profit, and for the safety and for the prosperity of the general public. And that's, I think, what the message we should continue sending. And I believe the climate community, of course, has every capability to do that. Thank you.